So, Joachim, please
Yes.
start and be on time.
Tu peux enregistrer, ça marche pas. Bon, c'est vrai. So, thank you for coming. This is not the echo I wanted. There you go. So this is the PhD defense for my work of the last 4.5 years, called Segmentation and 3D Reconstruction for Carbohydrate Estimation. So I am, as Stavrola said, Joachim Dehais. I'm a master student. Well, I was a master. I'm now a PhD student still for a few more days. And I work here at the Diabetes Technology Research Group. So let's get pretty much straight into it. What's the background of the project? This project started because we work with the University Hospital in Hospital, just on the other side. And they have diabetic patients. And diabetic patients, particularly type 1 diabetics, they are reliant on external insulin, so they have to inject insulin. Sometimes if it's not too bad, they can do it a few times a day, and sometimes they have a pump that does it continuously. So that's really tough. And to properly inject insulin, they need to count how much sugar they eat, how much carbohydrates. The problem is that this is very difficult and it takes a lot of time every day. But that's not, of course, just the case for people who have diabetes, it's just worse for them. But it applies to any person who wants to assess their diet and make sure that they eat properly. So this was the context at the start of the project. The question in itself was, can we automate that with some computer vision, which is trying to process images with computers and figure out what the content and what's in there, to use machine learning as well, and especially to use the smartphones that we find just about everywhere now. So the goal, both of the PhD and the project, is to use minimal user input and have the maximal nutritional output, which is as much information we can on the food. Looks a little like this. A nice photo from a pie that Sergey took, I believe, 4 years ago. The nutritional content and a little bit of magic in the middle. Now, of course, the magic we will explain, and it goes to answer 3 main questions. What food they're eating, where is it in the image, and how much they're eating. What 3 questions that we will not answer, however, we leave that to the dietitians and to the doctors, is who is eating it, why are they eating it, and what's the effect on their body. So knowing the goal, this is more or less what we have to answer. What the question of what the food is, where is it, and how much is there. That, of course, can be done in 15 different ways, and for that there are quite a few paper contributions by different groups. Most of them, however, focus on the recognition that I will not talk about because I was doing something else. They will also talk about the segmentation to a lesser degree, even less with the volume. And of course, there are maybe 2 or 3 publications that have a complete system for this. It's very few, and most of them are quite old. The youngest one is from 3-4 years ago. So we have these things, and we want to know what to do with this. So, in effect, what are the contributions of this work to the field? The first contribution, or rather, what the question is how did we organize this system? And this system, if we start from this, is organized in 2 different branches. The first branch will first try to answer where the food is, and then what kind of food it is. The second branch will start on the other side and try to calculate the size and the shape of the food to answer how much. And once we know how much we have and what type of food it is, it's fairly straightforward to calculate the nutrients. So this is just a very basic high-level one. What does that say in text? I try to keep it simple as well. It's essentially what I've just said. On one side, we try to find what it is and where it is. And on the other, we take our images and make a 3D model. Then we combine the 2. What the user sees, however, is slightly different. The user has their phone with an app. They take a couple of images with a reference card right next to the plate. Then they send them to us. We calculate where where the dish is, where the plate is, using an ellipse detection, but they don't see that. All they see are the results of the segmentation that come afterward. If they accept the segmentation, we go to recognition, and we try to figure out what food they're eating, and to ask them if they agree. When that is done and accepted, we build the 3D model in the background and combine that 3D model with the recognition into the nutrient content. But of course, we're not here to use it, we're here to see how it was made. And the system itself was made using a client-server architecture, with the back end on the far right, that is all the software that does the actual processing, the server in the middle that will organize a little everything, the files and the processes, and then the phone that connects to the server. In terms of amount of work, the interface was quite a fair amount because we needed to think about the users themselves and not just about our algorithmics and coding. Then the server, that was a little easier, but naturally I will hide it, but most of the work was when we worked on the back end and the software. And if we look at it, there are 5 steps. The dish detection, the segmentation, the recognition, reconstruction, and the nutrients. How much did I contribute to this within the project? The dish detection, I did it all. It's a fairly small piece of code, but it's very important at the start that it works. Then the segmentation, I did the majority of it, but Marius did quite a lot, especially at the start, and then to guide the rest. Recognition, just some maintenance and documentation. The reconstruction, I did pretty much everything, but Sergey also helped me at the beginning. And finally, for the nutrients, it was a bit of organization and maintenance as well. So, what did we do in the dish detection and the segmentation? Well, for the dish, it's a pretty classical thing. We have an image and we want to find an ellipse, the projection of the circle. So we find the edges, here shown in red. We have the edges and we want to find the dish itself, again shown in red. And the most classical way to do this would be to use random sampling, in this case, RANSAC. And this is how the algorithm works. We randomly take some points on the edges, create an ellipse from those points, evaluate it to see how many edge points it fits. And if it, in the end, essentially we keep the one that fits the biggest number of points. The problem is that this is not always very fast, and it's not always very robust either. So there is a system that is called GroupSAC that makes this much, much faster. And the way it does this is by grouping the edge points together by proximity. And once we have those groups, we can just take one group and create an ellipse for it, or 2 groups, maybe 3 groups. But because we take much fewer groups, the algorithm, the RANSAC principle, goes very, very fast. However, it's fast, but it's not accurate, because it's very sensitive to the way we group those data points. If we make them in too many small groups, it's equivalent to a standard RANSAC. But if we just make them in several big groups that contain too much data, then the algorithm doesn't work. So the idea was to use GroupSAC, but to replace the model generation by a second layer of random sampling. And so we add a fixed time RANSAC to generate the models within each sample. This way we are guaranteed to get an ellipse even when the grouping mechanism is badly selected. And that brings us to the segmentation. We have 2 systems for the segmentation. One is automatic, that's the standard one, and one is semi-automatic, so the users can design it for themselves. So this is the latest version. There were some previous iterations, but this is the best one at the moment. So the first step is we have those images, or just one, and we calculate a gradient map. But this gradient map is made in a very specific way, which is that there's a CNN trained to recognize semantic edges. So from this, we get to something like this, where in the black images and white outlines, we actually have CNN classified, well, CNN quantified semantic edges. And once we have this, on the other side, we consider the seeds of our algorithm, because we're going to use an algorithm that uses seeds. In the semi-automatic case, that's quite easy, because the user gives us the seeds. In the automatic case, we don't know where they are, so we just sample a regular grid. That works quite well, so we go to the next step, and we apply the seeded region growing. In the semi-automatic case, we are quite done, because the user selected those objects, rather they pointed them out. But in the automatic case, we still have a lot of work to do, because our regions are not merged yet. We still have a lot of regions that should be put together. And to do this, we add another layer, which is statistical region merging, and we'll take care of merging all those small regions into big, consistent ones. Now, these are very simple algorithms, and as a result, they work quite fast and happen to also work very well on the data set. But this is still just perhaps a simpler problem than the 3D reconstruction and the volume estimation. Because given an image, the patients can segment it. It's tedious, but they can do it. However, making 3D reconstruction and volume estimation is much more difficult for the patients than the rest. And here the key was that because we have such unruly patients, we need to adapt to whatever they do. And that goes through a number of essentially data correction steps, things that prevent the data from varying too much. And using those, we can set and tune the parameters fairly easily. The simplest case would be correcting the intensity range before selecting edges, well, before detecting edges or salient points. And that happens to help quite a lot, because if there's a contrast change or an intensity change, we don't have any problems. It still works exactly the same way. The next thing is to never really use a numerical limit, but instead to use qualitative values. When we match salient points between the two images, using a threshold on the distance between the features does not work so well. Instead, if we just choose the best symmetric features, we get something that is quite easy to understand, it's very fast, and it works better than with even a threshold on just the best global matches. But that's not all, and perhaps the main contribution to the 3D reconstruction is now, it's the qualitative selection of calibration models. And this goes by using what they call an a contrario model that I can explain, let's say, using physics terms. In physics, there is something in the universe called the background radiation. And the background radiation is essentially a small signal that we find everywhere in the universe and prevents us from getting any accurate data beyond this. So we cannot actually read the Big Bang or anything like that, because there is this small signal that stops us. And the idea is to create a background radiation for our model and to find those models that are so far from the radiation that we can detect them. And that goes by finding models that are perform very well on our data and very badly on the background noise. And the main tool for this is a fairly standard one, but not very used. It's called the false discovery rate. It's the idea that we want to have a model with as many inliers as possible with a very, very small pollution rate. And it works a little like this. We have an image with a number of, we have two images with a number of matches between them, shown as red lines here. And we want to create a kind of background noise in those matches. The easiest way for this actually turns out to be selecting matches at random. And we get something like this, where we match just anything with anything else. The result is that we want a model that works well on the left, but not on the right, because the right is chaos. And if we have this, let's say, ordered data on the left and chaos on the right, we want to compare the performance on the model of the model on the two of them. And the way of doing this is, for a given model and a given threshold, we look at how many inliers it has in the data and how many inliers it has in the noise. And we get a graph a little like this. So at the bottom, the inlier rate in the data, and on the left, the inlier rate in the noise. What we want here is to go as far right as we can, which is to have very high inlier rates in the data, but very low in the noise. And the best way to actually limit the pollution of the model using this system is to put a limit on the false discovery rate. In this case, the false discovery rate is quite easy to calculate. It is the inlier rate in the noise divided by the inlier rate in the data. So this is a very simple formula to calculate the pollution levels in your model. And compared to the previous methods, which I started with, well, which I took from publications and adapted to our problem, both the background noise model and the measure of noise deviation were better. So it's faster, it's easier, and it's better. That's win for everyone. Now, we still need to adapt to some other things. Once we have calibrated our system, we have to reconstruct the 3D model. And for this, we need to find a depth range. The depth range, like the matches, is found using ordinal filters. We just take the central 95% and eliminate all that's outside. This way, we don't actually ask any questions or fix the depth range. We just tell them, no matter where you use it, we will try to find the best way. And the second thing is to always try to process things and to bring things to the same size. Because the same size means the same scale, at least for most of the data set. And once we have the same size, the same scale, again, the parameters become easier to tune. And it's the same thing here. We fix the size of the area of the plate when we do the depth estimation, so that we are always approximately at the same scale between the different runs. But that's combined with a hierarchical reconstruction, which itself will look at multiple scales on this fixed size object. So we really capture a lot of things, but always more or less aligned between the different runs of the software. And finally, at the end, once we have the 3D mesh, we also give it a fixed size, and that way we don't ask too many questions or too much out of the processing. But this is fairly, I would say, standard. This is fairly general problems. What if we have some problem-specific ones? In this case, we have one. We have the plate. And the plate can help us to calibrate, because there are some tangential constraints. And it can help us to reduce the problem of stereo matching, because if we just match inside the plate, we actually reduce the load, and we also simplify the problem. And finally, we can use it, and this is probably the one that has the biggest effect on the software, we can use it to find the vertical orientation in the scene. But rather than me talking, let's have a look at some results. Here we have the results for the segmentation. But before, how did we evaluate that? We have an image database, about 750 images, all manually annotated, sometimes semi-automatically, depending on whether we got it from a user or did it ourselves. And out of this, 2/3 were for training, 1/3 for evaluation. For the metrics, we consider the overlap between the resulting regions and the true regions. that gives us a measure of precision, a measure of recall, and by taking the arithmetic mean, we can get an overall score that penalizes either over-segmentation or under-segmentation. Now, we actually have two versions of this score. The score that defines essentially the minimum performance per image, and the score that derives the average performance per image. And this is what we'll see in the next slide. Here we have not only our work, but some of our previous work and some of the work from our competitors on the far right. You can see on the left that the semi-automatic seeded region growing is the one that performs best. That's quite normal. Semi-automatic methods usually work much better than automatic ones. For the same thing, in the automatic section on the right, the new version works slightly better than the old one, and again, slightly better than the first one that we had. If we compare it to local variation has quite a few problems related to noise in the gradients, so it doesn't perform well. Now, I've put the links to the publications themselves. If you have the slides, you will be able to read them and check them out yourselves. But once we've done with the segmentation, what about the volume? In the volume, it's much, much more difficult to get data. We only have 77 dishes to test with instead of 750 images. That's because we need to use a commercial depth scanner, a very heavy algorithm, and to spend maybe a minute or two every time scanning, processing, and then an hour cleaning the point cloud and extracting the volume. So this takes quite a lot of time. And for each of these dishes, we also have to get the images from which we will test our software. So we take 3 image pairs per dish, and then to evaluate, we segment everything manually, extract the volume 8 times for each of the 3 image pairs for every single one of the 77 dishes, and we compare that to the ground truth obtained from the point cloud. The metric of choice here is the relative error. Now, there are a lot of systems that consider the relative difference and the standard deviation, but the relative difference has a lot of numerical cancellation, so we don't really see the actual errors. With this metric, the relative error, it's unforgiving. It will give you exactly how bad or good your system is. And the results that come with it are here. At the bottom, the system that we proposed and improved over the last 4 years. And then the top 3 are choices of representatives from the bibliography. So we have a single view estimation, a sparse multi-view, and another dense multi-view to compare with. Now, you can see that the single view doesn't work well. It's quick, but it has very high errors. That's fairly normal because they all use some very rigid notions of shape. And those notions don't really apply in our case. The sparse multi-view works a little better, but doesn't have enough definition. Then the dense multi-view works even a little bit better than the sparse, but it's still not as accurate. Now, in the difference between what we propose and the second best, about 4 or 5% are actually due to the way we extract the vertical direction. Because we use the plate, we have a very stable vertical direction. But this previous work, the dense multi-view, they were using the reference card, which in their case was 50 centimeters wide. In our case, the reference card is a credit card. So it's almost impossible to get an accurate measure of volume or orientation on such a small object. Now, this was published, like the segmentation, fairly recently. This one just a few weeks ago, actually, in the IEEE transaction on multimedia. But these are numbers on static data sets. And what we'd like to see are actually the effect on the people. So the effect on the people, we started fairly slow. We first took some dishes, 24, made some estimates for each of them, and compared to the ground truth. That was, let's say, the first foray outside. And for this, we got an average absolute error of about 6 grams, which is quite good. What we expected was something slightly higher, and what we wanted was to be no higher than 20 grams. So we're far below, and we can continue with this. And the next step was, of course, drafting a few patients themselves and comparing what they did to how well we performed. So we had 19 people a couple of years ago come in at the hospital. We gave them a few dishes to each of, we gave each of them a few dishes, and we asked them to first estimate on their own, then use our software and give us the results. Then after this, we compared to the ground truth that we had found, and we find that we do less than half the errors. We do much smaller errors than them, not just in absolute, but also in relative error, and also we have many more estimations that are close to the truth than them. So this was very nice for us because we could say we're doing better than them, so we should definitely go further. And because they themselves said they would use it, we had no reason not to go to a clinical trial. And this is how it was designed. For each of the patients, we had approximately 1 month of trial, 2 weeks of training with the software, where they weren't allowed to see the results, then 1 week at random, where they could either use the software fully or not at all, and then the next week was the other way around. So we had 20 patients for this, all type 1 diabetics, and it took a total of 3 months the year before, and we analyzed this little more recently in 2016 using data extraction software that we made here to not only integrate the patient data, that means the insulin pump, the CGM data, so the blood glucose monitors, the activity trackers, and the carbohydrate intake. So once we have integrated all this, we still need to run some calculations and find some measures of the patient's health. And for this, I implemented a whole lot of them. So we had 41 different metrics of the patient's health. And all of those, you can group them in about 15 different types, depending on what they measure. The result after the statistical analysis by the hospital was that using GoCalm, even on this small period, they had lower blood glucose, less deviation, less variation in their blood glucose, fewer hypoglycemias, and those two other measures are a little more complicated to explain, but essentially they signify that the variation is lower. Finally, after they eat, they actually had a lower average blood glucose, which is the most important thing for us. That when they eat, they have a good estimate of how much they're eating. So we like that very much, and that was a bit the pinnacle of the project, which says that we should start going a little further now, but because for me it is the end, I need to talk about a few other things. In particular, there were a number of things that I did during my project that either weren't included in the final product or were slightly off topic just to extend a bit what we understood of the problem. So the first one was tensor segmentation. Using the seeded region growing system that we have and the merging as well, we can easily extend it to n-dimensional matrices. And in particular, the goal was to apply this to lung segmentation, which is another project of the group. Now the problem is that this method was quite slow. For a 256 cube of randomized data, it was taking about 50 seconds. So the implementation needs to be revised before it's used for other things. Another thing in segmentation, however, that did work quite well was the iterative watershed. This is a clustering or merging system that is very close to the original watershed, or the waterfalls transform, with the difference that instead of considering a direct system, it's an iterative, repeated process. So, as you may know, the watershed is a fairly simple system where you group together points that have small differences between them. And that gives you small clusters. Then you have the waterfalls transform, which does this, but also gives you a hierarchy based on the difference of which small clusters to merge together. The problem of both of those is that they are very sensitive to gradients, and most of the people who use watershed and waterfalls actually smooth the gradients or apply some intermediate steps to prevent the noise from acting out. So the idea here was actually to make a simpler process and do an iterative version. So we create the clusters, we merge them, and from this we obtain a new graph, and we repeat the process on the graph. So it's a sort of compression system, where every time we take nodes in the graph and put them together, while updating all the distances and the costs. And that makes it much more robust to noise in the gradients. In fact, it performed almost as well as the region merging, up to a couple of percents. So we didn't include it in the final system, but it was very close to be. Now, in the reconstruction, of course, I tried quite a number of things. And the first one, the most recent one, was calibrating using a circle. So we know that if we have a circle with a fixed size and a photo of it, from the projection we can tell where we are. So to do the camera calibration with this, the numerical errors were ridiculously small. So we could use it very easily. The problem is, when we passed on to the actual use, to the plates and the ellipse that we detect, suddenly those errors jump. Actually, they're not errors, they're differences between the calibration we find using Ransack and the calibration we find using ellipses. So you think with such massive differences, we should be looking into what's wrong. And if you look at the volumetric errors at the end, it almost hurts you, because this is such a nice system, but in practice, we don't have the proper setting. And there are two causes for this. The one is that plates are not perfect circles. We just have quadrics that approximate a circle. So when we detect one, there is necessarily a lot of noise involved. But on top of this, you add the noise of detecting it and the algorithm that we use, and that certainly doesn't help this calibration system work. Then we have some very, very low-level numerical things. The first one of which was to condition the constraints on calibration models using linear algebra. In particular, it's the idea that if we do a QR decomposition of the matrix of constraints, then the better constraints would be those where the triangular matrix is close to diagonal. However, when we try to resample and to maximize this diagonal in the QR decomposition, it doesn't really work. It tends to oversample noise. And similarly, because we are in a close to planar scene, the calibration is very sensitive to noise. So there should be a way to compensate for that. And the idea was to give more weight to the points that we detect as far from the plane. So this is a fairly simple process. We just find a plane that is approximately in the middle and give more weight based on the distance. And that did have a positive effect, but it was so small that it was essentially not worth it to add it to the final system. Finally, oh, I'm sorry, that's not final. I found that there was a way to calculate the geometric distance to a fundamental or essential matrix using 7th degree rational polynomials. This is done through some simple algebraic work that I can describe later, or then more into the thing by approximating unit vectors using linear, well, the L1 distance. Then, in the dense reconstruction, and I believe this is the very last one of the side steps, I found that we could combine the normalized cross-correlation with the principle of the census filter, which is to look at the signal relative to the central point of the window. And this, it's called the centralized normalized cross-correlation, the centered normalized cross-correlation. And you can see here at the bottom, we have the matching costs for different horizontal motions illustrated in the intensity. So what we'd really want is to have white almost everywhere, but a black line following just the perfect match. And if we look at then the sum of absolute differences, which is the most basic of matching costs, it's a very smooth function. So it's actually quite difficult to see where the shape is. If we switch to the zero mean normalized cross-correlation, there's a little more contrast, but it's still quite difficult. If you go to the center normalized cross-correlation, you can start seeing this black curvy movement appear on the animation. But finally, the census filter works much better because it's white almost all the time, except for that sharp black line moving through the shape. In the volume, there were a couple of things to do, not particularly important, but I think they're interesting, so I'll put them there. The first one was the work I did at ETH while I was studying there, which was to use the plate models, or simple plate models, to reconstruct the plate from point clouds and to separate the food from the plate using this model. Then the last one, this is a bit let's say my favorite child. This is using semantics as a way to decompose a 3D model. This is essentially the principle of taking this very tasty looking cordon bleu, knowing how it is made, which is it's chicken with meat, well, it's cheese surrounded by ham, surrounded by chicken, surrounded by bread. If we know this, then we should be able to transform it into the, let's say, separate 3D models for each of the components. And that gives us a much finer granularity when we look for the nutritional content. The problem here was actually that nutritional databases don't even have that kind of accuracy. They're all very variable and not reliable at all. So even if we have a great system here, we cannot use it because the data to verify it doesn't exist. And the question is, what do I think we can do for this field for the future? Well, I don't despair that there is some fundamental work to be done. Yes, I have 4 minutes, 3 minutes, I know. That there is some fundamental work to be done, especially in automatic random sampling, multiple structures, using that function for the epipolar distance, and automatic tuning, as some would call plug and play, which often ends up being plug and pray that it works. Now, there are things in the segmentation. There is always work to do, especially with the advent of 3D and color cameras. There are, of course, multiple dishes, which I conveniently found an illustration for here, which is that we'd like to find the food in this mess. Of course, it's not going to happen anytime soon. Finally, there are some other more minor things like procedural modeling and the semantic structures that I mentioned earlier. But I think that's the main idea, that there are some ways to go, but it's not the low-level processing. It's the more advanced, at the same time more fundamental, but also more applied. So, to conclude, this work was a lot of system engineering and putting it all together to make it work for the clinical trials, amongst others. But there was also some work done in the computer vision. There was plenty of things to try and never enough time to try everything. So we did that, and we hope that it worked. Of course it did, quite well. Which brings me to the publications that have come out of this. I think you will prefer if I show them to you afterwards in the slide itself rather than list them. And this is to compare to existing publications in the field. I've only selected perhaps 1/5 of the total. Finally, I'd like to thank Professor Mugiakaku and both of you online in the United States, Professor Polifeis and Zveka, for helping me through this. The university hospital led by, well, the endocrinology department of the university hospital led by Professor Diem and Stettler. The Dr. Martin Gerber and Roche Diabetes, where I worked for 2 years. And finally, everyone at the Diabetes Technology Lab for suffering through my fantastic jokes. Now, I'd like also to thank everyone here for their attention, and if they have any question, they're welcome to ask them. Oops. Let's see what happens here. Okay, so we should now be able to hear you if you have anything. So if you have any questions?
Yes, so what is the procedure? Do I ask? Is this the right time for me to ask questions? Or?
Sorry?
I think that
Procedure is.
first the audience can ask questions.
Yeah, maybe
Yeah.
may I ask, Joachim? So
Mhm.
I wanted to ask about segmentation methods. So you know that recent years the graphs performed very good in segmentation and actually in rectification problems. So can you comment somehow if you look into graphs in this sense, or why they were rejected if it was?
Wait, I will cut the sound to prevent the echo. Okay. The graph principles, I always like them, but the problem is as soon as you go into graph optimization, the cost of the procedure increases so much compared to what we have. So because we use direct systems, okay, let's go here. Because we use direct systems, they're very quick at the cost of a little error. While those are very heavy, and they will give you a small advantage, but for a user application, it's usually not worth it, unless you can make it really, really fast. Any other questions?
Yeah, of course.
A timid one. What do you mean by you use
So
the
first,
term?
like on the calibration side,
Mhm.
so did you also, so you said that the edits could be very useful, but then in the end you had to discard it because at least the ellipse by itself was not good enough.
Mhm.
Did you also consider using, so if you use the phone, you always have the vertical from the relatively good, especially if people hold the camera still to take a picture, a relatively good estimate of the vertical, at least to guide you in the beginning, potentially even beyond that. Did you consider using that?
have the software for calibration using the vertical direction. I think it was one of your students who made the equations, but I have the software. The point is that the data set itself did not have this information. So if we wanted to proceed to a trial with it, we would have to make a whole new data set with the gravity data included. So I would love to get rid of the ellipse and to just go to general dishes or even no dish at all. But at the moment it was, let's say, a fortunate choice because it helped with a lot of the processes.
Okay, so did you prototype or try it or not really?
Sorry, did I prototype?
Well, like using the vertical or because the data set didn't contain it, you didn't go there.
As I said, I have the software, it's integrated, but it's not used because of the lack of data. That would be one of the next steps, and also to compare it to your software.
So then I was curious, so you already partially answered this to Matthias, but so here also I would like you to make the difference between saying that it's not practical and then then forget about the practical context and just look for what would be the advantage if we can forget about the limitations of computations. So in particular, for the segmentation, where if you can use graphs and so on, you could even use, so we've been exploring that, use 3D volumetric segmentation for the food immediately. So do something that we have tried in different cases, essentially a joint reconstruction and segmentation approach. So how would you? So I know you'll say that this was not practical and would be beyond the computational resources that you have. But ignoring that, what would be the potential advantages that you see? I hope you're familiar with that work where we do both things together, segmentation and 3D reconstruction. How do you see? Could those technologies be used here? What would be the advantages? How could you somehow make use of this kind of research if computations were not an issue, which of course they are?
I think it joins, sorry, I'll cut this out again. I think it joins a bit the semantic processing, which is as soon as we include a little more information into it, we can get better results for both, that's for sure. It's true that the moment may be a bit slow, but if we ignore this, the results would certainly be helpful. I think perhaps more in the more if we include the recognition than just the segmentation. You might have seen at some point. Sorry.
Once, yes.
So I had the sound muted to prevent the echo. You were trying to say.
We don't see the screen anymore right now.
You don't see no. Someone turned it. Yes. Okay. No, it's. I think it's a very good thing, but there's more to gain from introducing the labeling and the recognition than just the segmentation. The segmentation will, of course, make the 3D reconstruction and the 3D segmentation easier. But if we add the label and the type of object, then we can constrain the shape better.
So yes, so this was one of the things I was wondering. So with the food, some of the food, like in the layout, or how much can your system take into account the layout of food that, for example, there's dishes where, let's say, spaghetti and you put sauce on top, if it's not mixed yet, then how do you somehow estimate the relative volumes
the system at the moment does not, but this is why I want to add a little more about the semantics, which is to put the relations between the food in effect. The case of the sauce on top of the pasta has always been there, and aside from knowing that, say, we have sauce and we have pasta, it's very difficult to say this one doesn't go down to the bottom of the plate. We need a little information from the human in this case.
So this is where volumetric segmentation could, like there would be possibilities to incorporate that relatively easily in a volumetric segmentation. Of course, I understand it is a lot more expensive. So
Yeah, the idea would have been. No, go ahead.
right now, possibilities, of course.
The idea was originally to start in something simpler, which is to have the reconstruction and then use the semantics to segment the 3D volume directly. So this would have been much cheaper, but of course not the same quality of results.
So in terms of capturing, for learning, one of the big challenges is, especially if you want to go now, everybody's using deep learning and so on, you need essentially a lot of data. And so you can collect some finite amount of data. How would you imagine going beyond that? Like how would you imagine scaling the data capture, and also in ways that you could potentially gradually extend to food from other cultures and stuff like that?
To extend the easiest way is to get users, of course, and to have a sorry.
How would you go about getting users to contribute in an effective way?
Well, the easiest way, which we are still talking about, is going with a company that has a benefit in spreading this kind of software to their users. And then, as they spread the software, first it doesn't do a lot of things, but just it captures a lot of data. And as it captures data, you can train your systems and extend the software for the users. And as you extend the software available, you will probably extend the user base in turn.
So how do you get the user in the end to kind of provide the information, or like there would be a careful UX design, I guess, to have that be effective and not frustrating to the user, right?
Yes, that's why it took so long to work on our user interface, because we tend to design some very, let's say, engineered things, but the user wants as little to do with the software as anything. So the way it is designed, it's not visible here, but let's go back up and to the user view. Okay, the way it is designed, if I can see that on the screen. Okay. So the way it was actually designed by some specialist UI designers, and the idea behind it was to put as little information as possible on any screen, just one major point, and then yes or no. Essentially, almost just a binary system where the users had as little choice as possible. Because if we give them too much choice, and this is what happens, they tended to use it for the wrong reasons, because we cannot control the users. So one of the things I did on the user interface was actually to remove almost half the options that the users had, so that they would just keep going in one direction, the one we wanted, or rather the only one we could handle at the time.
Okay, good in questions.
So it's Victor, perhaps you have some questions?
Yeah, I have maybe one kind of high-level question that I was just curious
That's actually a very difficult question to answer because I have asked this question to the physicians, and themselves they're not quite sure for many of those indicators what is the optimal value. So I would say for many of them, say for example the standard deviation and any notion of variation, if it goes lower, it's better. But they do not have, let's say, a fixed value in mind where all the patients have to go there. There's another indicator which is called the HbA1c. It wouldn't have varied on such a short period, but it keeps a memory of how much glucose you've had in your blood for the past few months. And what they want is usually to put this as low as possible. But they know that if they push the patients too hard to go low, then they risk hypoglycemias, and this can be coma or hospital or even death. So they are rather conservative in what they tell people to do as well.
Mm-hmm. So, I mean, in the end, I'm curious to understand about, how good your system is now, or how much better it could be. Even if you, let's say, I'm trying to understand, even if you could improve your estimates by, a certain amount of, a certain percentage or something like this, what is the potential benefit that you could still get for these health indicators? Do you have a sense of this? Is the system just good enough now and there is nothing significant to gain? Or if it were more precise, could you actually get even much better outcomes in terms of the health indicators? Do you have a sense for that?
There is one thing, and it's that they measured for, I think it was for children, but also adults. No, actually for adults as well. If you make an error of more than 20 grams in your estimate, you will have a very large difference in your blood glucose. So 20 grams is sort of the really last resort error. If we can do better than that, okay, but if we do worse, that's really a problem. Then the closer we get to, say, a perfect system, the less effect we will see, because all the other variables in the treatment will take control of the problem. Because what we give is really, well, it's not the smallest portion, but there are so many things associated with diabetes and a proper diet that just giving them one estimate will not change all the other habits that they have. And once we get that perfect estimate, it will be up to all the other things that they do right or wrong.
Yeah.
So the studies Matthias, the studies have shown in a rather big population that if we consider only that the food impact and influence the glucose control, then we need to have an error less than 20 grams per meal. Because otherwise the glucose profile after the meal intake is influenced in a way that it is elevated, extremely high, and if this happens every day, and particularly in every meal, then automatically the risk of a person to have cardiovascular disease is increased drastically. So the aim of this kind of system is to have the postprandial glucose profile as close as possible in the normoglycemic area. So the area which in the case of postprandial glucose is below 180. And this is also the guidelines from the FDA. So, by the end of the day, we need to have a system able to bring the glucose profile back to the threshold of 180 mg per deciliter up to 3 hours after the meal.
Okay. Maybe just a last high-level question. So going forward, what do you think will be the biggest challenges to actually deploy deploy such a system in practice? Is it still technical stuff like the speed of the system or the accuracy of the estimate, or is it more just in terms of the user experience that is still difficult? What do you think are the main practical challenges that you would face when deploying such a system?
I would see two challenges. On the accuracy side, as we get more types of food, we will need software that is able to work in more complex situations. One problem, for example, is reflections. And as you know, when you have reflections in a scene, it's much more difficult to build an accurate 3D model, and in this case, to calculate the volume. The other side is that nutritional databases are absolutely not homogeneous, and most of them don't follow the same principles to estimate the content, or even if they do, they usually have different results because it's a different geographical area. So we have, of course, things that are tied just to the software, but I think the main problem will be everything that is not part of the software, which is databases, multiple cultures of food and how they're eaten, and the actual content that we don't really know that well.
Okay, I think that's it from my side.
So, has anybody of you any other question? No. So if that's the case, so I would like very kindly to ask you
To leave.
Yes.
Okay, so thanks very much to the two of you for your call. Sorry, yeah, thanks very much. And I'll be
qualifying speaker will stay.
Yes,
you
but
will go out and
I'll-
you will come again back.
but I'll thank them first and
Yeah.
then leave.
You'll come back.
So I'll be back later.